Okay, so to do this problem, this is problem number 36 and let's see, it's in the complex zero section. In the version 2, I'm sorry, that's the clipped version. Yeah, section 3.6 in the second edition. It's also 3.6 in the extended edition. Is it 1.5? So we have to break this out. They're telling us to completely factor it over the real numbers and completely factor it over the complex numbers. So there's a lot of tricks we can do to do this. One thing that a lot of people will do, they'll graph the function. So here I graphed this. Let me go back to this. I graphed this function. I'm seeing a fourth degree equation, which I expected. I'm also seeing a double root at x equals 1, because it bounces off the graph. So that tells me there's going to be two real zeros, and they're both going to be 1. And then there must be a couple of complex zeros, and we have to find them. And so how do you do that? Well, let's see. Let's come back here. So actually, Cauchy's bound and the rational root theorem, if you can't graph it, you don't have any idea what's going on. Those are good tricks to remember. There's another one that's a good trick, is Descartes' rule of signs. I won't go into that for this video since we already kind of know what the graph is. And in 2020 or in 2017, I think it's probably a safe bet we can just go with this route. So I saw my graph that x equals 1 was a 0. So I'm just going to use some synthetic division on this. I mean, I could certainly use long division, but since I know 1 is a 0, I'm just going to use the synthetic division. And remember, you pull the coefficients off the polynomial, and since I'm not missing any powers of x, I don't have to insert any placeholder zeros. If you're looking at that number 36, you see I'm just pulling the coefficients off. And then if you are having trouble remembering how to do synthetic division, bring down the 2, and you multiply. 2 times 1 is 2. And then you add these two numbers, and -7 plus 2 is -5. Then I multiply again. I'm going to get -5. 15 minus 5 is 9. Then 9 times 1 is 9. -15 plus 9 is -6. -6 times 1 is -6, and 6 minus 6 is 0. So we knew x equals 1 was a 0 because we looked at the graph, and here with a remainder of 0, we know it is. So then we know that x equals 1 was a double root because it bounced off the x-axis. So I'm just going to run the second root, the second value of 1 through, and just do synthetic division. Again, bring down the 2. 2 times 1 is 2. -5 plus 2 is -3. That's going to give me -3. That's going to give me +6. 6 times 2 is 6 times 1 is 6. -6 plus 6 is 0. So what I've got so far is x minus 1 times x minus 1, or I'm going to write it as x minus 1 squared. And then since I originally started with an x to the 4th function, and I've divided off x equals 1 or x minus 1 twice, I'm going to have a 2x squared minus 3x plus 6. Now, I would normally try to factor this, but since I already looked at the graph, I know it never crosses the x-axis again. I know these are going to be complex solutions. So all I'm going to do is I'm going to apply this quadratic formula. All right, x equals -b plus or minus the square root of b squared minus 4ac all over 2a. I know you've done this before. So for this part of this polynomial, a equals 2, b equals -3, c equals 6. And I'm just going to apply that into the quadratic formula. So -3 is 3, plus or minus the square root of -3 squared is +9, minus 4 times 2 times 6, all over 2 times a, which is 2 times 2. So that leaves me 3 plus or minus the square root of, let's see, 9. 2 times 6 is 12, times negative 4 is negative 48 over 4. And that will become 3 plus or minus the square root of negative 39 over 4. And of course, 3 times 13 is 39. Neither one of those is a perfect square, so we can't break that down. We can pull the negative 1. Remember, this is negative 1 times 39 that's underneath the square root. And I can treat it as 2 separate square roots because I'm multiplying them. And then we know the square root of negative 1 is I. So that means I can write these as factors as 3 plus I square roots of 39 over 4. I can also break this out as 2 separate fractions, right? And then the other one's going to be 3 minus I square roots of 39. And again, I'm going to write those separate fractions over 4. Now, they're looking for linear factors. So what do I do from here? Well, let's see. I guess what I'm going to do is I'm going to just clean this up. I was going to get fancy. Let me get rid of this work here. And since we're looking for linear factors, I really should be writing x minus 1 times x minus 1, though I don't think it's wrong to leave it as x minus 1 squared, but they are talking about linear factors. And then since I know x equals this and x equals that other complex number, to write them as a linearization, I can either write x minus the quantity 3 over 4 plus I root 39 over 4, or I could distribute that negative through. I mean, either way works. And then the other linear factor is x minus 3 over 4 minus I square root of 39 over 4. So this is the factorization over the real numbers and over the complex numbers for this polynomial. Hopefully this will help you do this again in the future.